Okay, where we left off was we were about to go over atomic solids. We saw the types of crystalline solids. There are molecular solids and ionic solids, and now atomic solids. This is where things get interesting because there's more than one type of atomic solid. There's non-bonding, metallic solids are also atomic solids, and network covalent solids, which is kind of like molecular solids, only it's basically they constitute molecules, but the molecules are kind of bonded to each other, as well as the atoms within the molecules being bonded. And so the properties are actually quite different from molecular solids. So first of all, non-bonding atomic solids are the types of solids that have dispersion forces only. And from that, you can probably gather that they're fairly weak. They have low melting points. And these are basically confined to the noble gases when they're in the solid state. So solid noble gases, particularly the bigger ones like xenon, which is relatively easy to freeze as opposed to the smaller ones like helium. Metallic solids have metallic bonds. You know, that's the situation where you have essentially a three-dimensional network of the nuclei of metal atoms, and they're surrounded by almost like a sea of very mobile valence electrons. And that makes them very strong, and it's also the reason why they can conduct electricity, is that those valence electrons can move around very easily. The melting points for metallic solids vary quite widely. There are some metals like, say, cesium, which would melt in your hand if you were brave enough to hold it in your hand, because it also reacts very violently with moisture. So it would suck the moisture out of your hand and explode if you held it in your hand. But if you did, it would melt because it has a very low melting point. And also you have metals like, say, iron, which has a melting point of something like 2,000 degrees Celsius, and others like, say, tungsten, which have melting points of, you know, something like 3,000 degrees Celsius. And so there's a very wide variety of melting points for metals. And these are metals. So, you know, think of a metal, and that's an example of a metallic atomic solid. So gold, silver, copper, iron, aluminum, you know, whatever, the metals, basically. For network covalent solids, these have covalent bonds, not just within the molecules, but essentially covalent bonds between the molecules also. So essentially you've got molecules that are kind of bonded together. And that's what makes for high melting points. And a good example of this type is quartz. Quartz boils down to silicon dioxide if you sort of look at the overall structure of it and take the lowest whole number ratios of one element to another, it comes out to be SiO2. But actually what you've got is silicon and oxygen atoms that are bonded to each other beyond just the combination of one silicon for every two oxygens. Those oxygens can be bonded to other oxygens and other silicons in essentially neighboring molecules. And that's what makes the network covalent molecules so strong. And so to look at some of these in a little more detail, the molecular crystalline solids, they're made up of molecules at the lattice points. Some examples would be ice, or solid H2O, and also dry ice, which is solid CO2, are both examples of this type of compound. They ultimately are held together by intermolecular forces that vary with the type of molecule. So if it's dry ice, the molecules are CO2, and you've really got nothing but dispersion forces. And that's why dry ice leaves the solid phase at a very low temperature and sublimes directly to solid if you're at atmospheric pressure, or can become liquid carbon dioxide if you're at a pressure of 5 atmospheres or greater. For regular ice, it's made up of H2O molecules, so you have dispersion and dipole attractions and hydrogen bonding. Because remember, you can have more than one type of intermolecular force going on at the same time. Everything has dispersion forces. The question is, does it have anything beyond that? For dry ice, because it's carbon dioxide, the answer is no. Dispersion forces, all that's got. But ice is made up of H2O molecules, so you not only have dispersion forces, but dipole forces and hydrogen bonding as well. And because of most of them have fairly weak intermolecular attractions, even in the case of ice, the water molecules are relatively far apart compared to liquid water, and so that weakens the attractions. And these solids usually have relatively low melting points. In fact, as low as the melting point of water is, it's relatively high for this type of compound because of all of the hydrogen bonding that water undergoes. So hydrogen bonding can raise the melting point some. And so the ionic crystalline solids are made up of cations and anions at lattice points. The crystal structure is one that maximizes the coordination number. Oh, XTAL is an abbreviation for crystal. And different crystal structures and you want to maximize the coordination number because more interactions between cations and anions lowers the potential energy. Different crystal structures can be found for different ionic crystalline solids because of the different ratios of the ions involved. It may be a 1-to-1 ratio like in NaCl, or it may be a 2-to-1 ratio or a 1-to-2 ratio like in CaCl2 or something like that. And so different ratios might have to adopt different crystal structures. Also, the relative sizes of the ions can determine which crystal structure will be the one that maximizes the coordination number. Okay. Sometimes you don't get a pure crystal structure of exactly one type or another. It might be somewhere between a couple of types, or it might actually even be a situation where you have one particular type of crystal structure for one of the ions and maybe the same crystal structure for the other ion, and they're kind of superimposed on each other. Okay, so that and the ratio of cations to anions in the formula can affect which crystal structure will be adopted for a given compound. Generally speaking, the more similar the sizes of the ions are, the higher the coordination number will be. But of course, there are some compounds in which the ions are just not nowhere near each other in size, and that's just something you have to deal with. As an example, cesium chloride has similar sized ions. The cesium ion and the chloride ion are about the same size. And what you find is that the chloride ions are in a simple cubic arrangement. With cesium ions at the body center. So it's sort of a body-centered cubic unit cell, only the atoms are not all the same, like we saw when we first looked at a body-centered cubic structure. The coordination number is 8. And if you look at the total number of chloride ions inside a unit cell for this compound, it's going to be 1/8 of an atom per corner. And it's a cubic unit cell, so there are 8 corners. And that means that there's 1 chloride ion in each unit cell. And if you look at the total number of cesium ions in the unit cell, there's 1 at the body center. That 1 atom is entirely within the unit cell, and that's 1 cesium ion. And so that's a 1-to-1 ratio, which it should be because it's CsCl, and it's also charge neutral, 1 positive and 1 negative, all together within each unit cell. Sodium chloride is an example of a common ionic compound where the ions are fairly different in size. The chloride ions are quite a bit bigger than the sodium ions. And so the coordination number is 6. And it's limited by the number of chloride ions that can fit around the little sodium ions. So chloride ions are at the lattice point of a face-centered cubic unit cell. And the sodium ions basically fill the gaps between them. Which actually, the sodium ions themselves are in a face-centered cubic pattern if you look at them, and the chloride ions would be filling the spaces between. And what this means actually is that you've got two face-centered cubic unit cells that are kind of superimposed on each other and offset by a little bit. So you've got face-centered cubic for Na plus and Cl minus simultaneously. With each unit cell offset a little bit from the other. So that's yet another way of looking at it. If you look at the total number of chloride ions in the unit cell, again, it's going to be 1/8 times 8. 1/8 of a chloride ion per corner times 8 corners equals 1 Cl minus. And if you look at the total number of sodium ions in the unit cell, the way the sodium ions are arranged, if we're looking at this as a face-centered cubic arrangement of chloride ions with the sodium ions in the spaces between the chloride ions, then what you would have would be 1/4 of each sodium ion per edge of the cube. And there are 12 edges of the cube. Plus, there's one in the, plus there's one in the body center. And that means 1/4 times 12, that's 3 plus 1, that's 4 Na plus. And what I forgot was the other chloride ions. You've got 1/8 of a chloride ion per corner times 8 corners, plus there are others. You've got 1/2 a chloride ion per face, because it's face-centered cubic, and there are 6 faces. So this is 1, the 1/8 times 8 makes 1 chloride ion. 1/2 times 6 makes 3 more. So that's 4 chloride ions. And so there you go. 4 to 4 is the same as 1 to 1. So it's a 1-to-1 ratio also. There are other compounds that adopt the same structure as sodium chloride, lithium fluoride, calcium chloride, potassium chloride, potassium bromide, silver chloride, magnesium oxide, calcium oxide, among others, have the same structure. Then we have what's known as the zinc blend structure, which is zinc sulfide. This has an even bigger difference in the ion sizes. The sulfide ion is way bigger than the zinc ions. And there's a figure of this on page 498. 1153. Here is a unit cell of cesium chloride. Here is a unit cell of sodium chloride. So you can see the chloride ions at the corners plus one at the center of each face. For the sodium atoms or ions, you have a quarter of them within each unit cell, and there's one in the center of each edge. So it's going to be 1/4 times 12 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. And plus there's the one sodium ion at the very center of the cube. So that's how you get 4 and 4 for the chloride ions and the sodium ions. And here is the zinc blend structure, which is very complicated. So I'm not going to spend a lot of time looking at that. So we'll go and look at some of the features of it, though, because they're fairly common. A lot of things take this structure. The sulfide ion occupies the lattice points of face-centered cubic. With zinc ions in half of the holes under each corner atom. These are called tetrahedral holes, and what the tetrahedral hole means is that there's one atom above and 3 atoms below. So it basically makes a 4-sided space within the atom. If you want to look at the number of sulfide ions in the unit cell, that's going to be 1/8 times 8 plus 1/2 times 6, which is 4 sulfide ions. The number of zinc ions in the unit cell is going to be 4, and each of those is entirely in the unit cell. So again, it's 4 to 4. It's charge neutral, and it has a 1-to-1 ratio overall. This structure is also found for copper 1 chloride, CuCl, silver iodide, cadmium sulfide, and some others. There is another situation where quite possibly the ion ratio is not going to be 1-to-1. In fact, there are a lot of ionic compounds where the ratio is not 1-to-1. We don't really have the time or the space or the will to look at all of them, but a couple important examples would be, for instance, fluorite, which is calcium fluoride. And that's 1154, figure 1154 on page 499. Okay, now we're getting really some really whacked out structures here. Calcium would be the gray spheres, and the fluoride would be the sort of greenish yellow spheres. And there's your arrangement there. So yeah, no problem. Nice and simple. Important facts about this is we have the calcium ions are at the lattice points for a face-centered cubic unit cell. Fluoride ions are larger, and they're in all 8 tetrahedral holes. Again, a tetrahedral hole is just the space where you have 1 atom above and 3 atoms below. And so the total number of calcium ions is going to be 1/8 times 8 for the ones at the corners, plus 1/2 times 6 for the ones centered at on each face, which gives you 4 calcium ions. And the total number of fluoride ions is going to be 8. All 8 of them are entirely within the unit cell. And here you get a 2-to-1 ratio, which overall is CaF2. It's charge neutral because you've got 8 negative charges and 4 times 2 or 8 positive charges. And so that's your arrangement. Lead fluoride. All right, let's try that again. Lead fluoride takes this structure, as does strontium fluoride and barium chloride. Among others. There's also a structure known as anti-fluorite, the anti-fluorite structure, if the cation to anion ratio is the other way around. Because up here we had a cation to anion ratio that was 1:2. So what if it's 2:1? Well, then in most cases you'll end up with the anti-fluorite structure where the cation and anion positions are reversed. Okay, I see we're at 30 minutes now, so I'm going to come back for one more segment, although we're almost done with this chapter. So the next one won't be very long. Anyway, we'll see you in a moment.